Hi, I'm Gustavo Exel, and today I'm gonna present a work that aims to facilitate the solution of coupled systems of partial differential equations using the element-based finite volume method, offering another tool for students and researchers that allows them to learn about the method without having to implement all the details of the mathematical formulation, and providing an easy and quick introduction to the computational solution of physical problems, which brings a fast learning curve to the user. This work wouldn't have been possible without the support and guidance of the professors Hermínio and Malisca. Briefly going over the agenda, I'll talk about the advantages of the library and its contribution to the community. I'll show how it works and how to use it, as well as the opportunities for customization by the user. And finally, I'll show practical applications that can be done using the library. Among the advantages of this library is the educational value that a simple and concise library offers, and the ease that the Python programming language brings to new users. The library also offers a great advantage for coupling differential equations, as this task presents several opportunities for programmer error when implemented manually. Another useful ability of the library is the possibility of modifying the solver script, so that the researcher can implement features that aren't in the library, with the head start of creating the script of a few hundred lines, which implements at least part of the problem depending on the specific limitation. Also, the solver uses PyEFVlib, a library that allows the reading of meshes, the creation of geometrical entities required by the element-based finite volume method, and the ability to save the results. Quickly explaining the library's workflow, the user provides the differential equations, which the library then interprets and generates the appropriate objects for each term. Then, the differential equation is discretized using the element-based finite volume method, and the terms are arranged so that the solver assembles them into a linear system. Then, the solver is assembled into a solver.py script, and the solution is generated in the XDMF and CSV formats, which can be opened using ParaView and Excel respectively. Here we can see a practical application of the library using the example of the heat equation. As you can see, the code is very straightforward. We provide the differential equation or differential equations in this list, and the list of unknowns, and all of the properties. Then the user informs the boundary conditions, where the name of the boundary is created in the mesh, which is generated using the open source software Gmesh. Lastly, some of the parameters are passed, some of which are optional, and more information about their use is described in the GitHub page of this library, shown at the end of this presentation. Finally, the run method generates the solver script and runs it. If the user wants to simply write the solver.py script, modify it and run it, then the method used is model.compile. Again, more information can be found in the GitHub page github.com/gustavoexel/bellbird. After running the code, we'll get a few files, a results.py, which is the solver, a results.csv, which can be read using Excel, Pandas, or basically any spreadsheet software, and a results.xdmf file, which alongside with results.x5 can be read using ParaView, where we can, for example, render this color map shown here. Here I brought the solver script in order to show you how is the structure of the solver, so you can understand which kind of modifications can be done and how you can do it. I'll go through it very briefly though, so that you can get a rough idea of its structure. I divided it into 5 sections. The first section being where we define some useful variables for future use. The second being the matrix assembly of the linear system, and where we can find all the terms of the equation which went into the matrix. Notice how each term is commented above its implementation. What the library does is recognize patterns which have been programmed previously. Take the diffusion term for example, k times grad of t. Bellbird already knows how to implement the surface integral of a scalar times the gradient of a scalar field, and so it's implemented below. If you're trying to implement a term which hasn't been previously implemented, you can check the bibliography at the end of the presentation, or for a short explanation you can visit github.com/Gustavo Exel/pyefvlib, which is the library responsible for the EBFVM implementations. Then, similarly to the previous section, the third section implements the independent term assembly, and the fourth section implements the transient loop and the direct solution using the matrix and the independent vector. Here is where the user might want to implement an iterative method for solving the equations, especially if the equations are nonlinear. Another useful information is that if the sparse parameter is set to true in the Bellbird script that generated the solver, the same implementation of the problem will be done, but using SciPy sparse matrices. Finally, in the last section, the boundary conditions and properties of the medium or media are provided to the solver. Here we have our first practical application. We have a cantilever beam which receives a load at its end. Here we can see Newton's second law applied to the beam, where its acceleration is zero, and the forces applied to it are internal forces which follow Hooke's law and the body forces. Notice again the simplicity of the implementation, with the possibility of visiting the solver code and learning from it. Another application that can show the potential of the library to couple different physics is the porous medium filled with slightly compressible fluid. The internal stresses of the medium are supported by the pore structure and the internal pressure. As load is applied to the medium, the pore pressure increases, resisting the applied load. Here we have the conservation of mass of both solid and fluid phases, using the compressible formulation, where the BO modulus m already contains the compressibility of the fluid and solid. The velocity of the fluid with respect to the solid matrix is given by Darcy's law. We are also applying Newton's second law of motion, or conservation of momentum, where this time the internal stresses are supported by the stiffness of the porous medium and the pore pressure. Body forces are also considered. The Cryer sphere problem is a classical problem in geomechanics, used to validate implementations. Here, only an eighth of the sphere is considered. And using the symmetry of the problem, we set the pressure at the outer surface to zero, and both the pressure gradient and the normal displacements at the flat surfaces are set to zero. Finally, the shear stresses at all faces are zero. Tracking the internal pressure over time, we get a pretty good fit to the curve, only get worse accuracy at the beginning of the transient regime, but considering the logarithmic nature of the problem and the time axis, this isn't anything to worry about. Thank you CILAMCE for giving me an opportunity to present this work, and again thank you to all the SINMEC people involved in the project.